Mission Control is live. What you're looking at is a fully integrated hardware-software system built on an FPGA, deployed to the cloud and accessible from any screen in the room. This is not a simulation. Every element you're about to see is running in real time. Three operational layers, three objectives. Layer 1, the pink FPGA board. Hardware intelligence, maze solver, ghost controller, voice command unit. Every move, every decision, it all originates here. Layer 2, the command server. A Flask application deployed on AWS EC2. It holds all live state. It processes every incoming signal from the board and serves the mission interface to every connected display. Layer 3, the displays. Any browser that connects to the server receives a live feed of the mission, updated every 200 milliseconds. No page refreshes, no delays. Supporting all three layers is the AWS DynamoDB. 6 tables logging every game result, every maze layout, every ghost movement, and every voice command issued during the operation. The Maze Runner. The FPGA generates the maze using Kruskal's algorithm, a spanning tree approach that guarantees exactly one path between any 2 points, a perfect maze built entirely in hardware. Imagine starting with every cell completely walled off, a full grid of isolated boxes. Kruskal's then takes all the internal walls, shuffles them randomly, and works through them one by one. For each wall, it asks a simple question. Are the 2 cells on either side already connected? If not, we knock down the wall and join them. If they are, we leave the wall standing, because removing it would create a loop, and we don't want loops. We keep going until every cell is part of one single connected region. The maze is complete, unique every time thanks to the random shuffle, and solvable by construction. The maze solver runs entirely on the FPGA's programmable logic. No software, no processor involvement. Maze data arrives over AXI-DMA as 100 bytes, 1 per cell. AXI-DMA offloads the transfer entirely to hardware, giving high throughput streaming with zero CPU overhead. The core runs a finite state machine through 3 phases: distance propagation, flooding the maze outward from the start, and assigning every free cell a step count. The backtrace. Once every cell has a distance, we walk backwards from the goal, always stepping to the neighbor with distance -1. Finally, we reach the output. The shortest path is confirmed. We implemented 2 algorithms and compared both in hardware. First, we did BFS, breadth first search, which floods uniformly in all directions. It just explores every reachable cell layer by layer until it finds it. It's guaranteed the shortest path. Second, we did A-star, which is smarter but heavier. It uses a heuristic, Manhattan distance, to prioritize cells that look promising, steering towards the goal. Each computed move is transmitted as a post request to the command server. The server validates the move, updates the rover's position in state, and broadcasts it to the display. The browser reads that state 300 milliseconds at a time and redraws the grid. The grid is a flat string of zeros and ones, 0 for open path, 1 for wall. Every move is confirmed, every position is logged. Once the path is found, the mission is complete. All the steps to reach the objective are confirmed. Now moving on to the vision system. We have a camera mounted on the wall at an angle, looking down over the grid. The raw frames pass through a 2x1 downsampler via VDMA. Pixel count is reduced by 75%. The CPU load is kept low. 4 red markers sit at the corners of the maze. OpenCV's HSV color detection locks onto them, calibrates over 30 frames, then crops and perspective warps the image, correcting for the camera angle and producing a perfect top-down square view. With the view corrected, the system tracks 3 pieces of blue tape on the grid. The frame is quantized into a 10x10 grid. Then the X and Y coordinates of the 3 largest blue blobs are reported to the server in real time. The position is confirmed. The coordinates are transmitted. The arena. Before deployment, each agent identifies themselves. Call sign entered here is logged against every result, permanently in the cloud. 13 columns, 7 rows, 6 coins, 4 threads. The rover becomes Pac-Man, user-controlled via physical controller. Each move validated server-side on AWS before it's physically executed. The rover's objective is simple: collect all 6 coins. The Ghost's objective is simpler. They don't need to collect anything. Ghost 1 is active from the moment the first move is made. Ghost 2 activates at 15 seconds. Ghost 3 at 30. Ghost 4 at 45. The longer this takes, the worse the odds. The ghosts run entirely on the FPGA. 4 ghost instances in programmable logic. Each one takes the ghost's grid position and the rover's position as inputs and outputs a direction every clock cycle. We have 2 modes. One is the line of sight. If the rover shares a row or a column with no intervening walls, the ghost charges directly. Otherwise, we have the wall following, which is priority order based on current facing direction. Forward, right, back, and left. We have the 3 pipelining stages. First is the line of sight computation. Second is the wall check, and third is the direction selection. 2 nodes. Node B is the rover, executing the controller's moves. Node A runs the 4 ghost instances in hardware, reads the positions back over AXI-Live, and relays them to AWS. AWS is a single source of truth. Maze state, rover position, ghost positions, all stored and served from the cloud. Both nodes stay synchronized through it. The live display is just reading that state. These are the 2 outcomes. Critical contact. The mission is over. Status written on the leaderboard. Agent name, run number, time taken, coins collected, and of course, the outcome. The mission is complete. The leaderboard is updated. And the most effective agent is always at the top. Now let's move to the voice control unit. It is deployed on the pink board. The system runs a continuous audio loop, 3 seconds of recording, processed and then sent to the recognition engine. When a valid command is detected, the board does not redirect its own screen. It contacts the server directly. The command is transmitted to the server's set page endpoint. Every browser currently connected to the mission interface polls that endpoint every second. When a new destination is received, all displays redirect simultaneously. The server clears the command immediately after the first successful read. 1 command, 1 redirect. Displays can be navigated manually afterwards, without any interference.
Arena. Archives.
Every command issued is logged to the voice commands table in DynamoDB, timestamp, command label, and the raw transcript of what was heard. Here we have 6 tables, and they are all operational. The leaderboard holds every mission completed, whether that is a win or a loss. It is sorted by the coins collected firstly, and then by the time. The system handles the legacy of the records automatically. The maze table archives every grid layout ever synced on the FPGA. Each one is recoverable and viewable in the archives page. Ghost logs and rover logs capture movement telemetry for every session. Vision positions holds a single live snapshot, always the most recent frame from the camera system. Voice commands logs every spoken instruction within its timestamp. The rover features a custom 3D printed chassis for the pink board, which acts as the main controller and is powered by a 10,000 mAh power bank. For the movement, the rover uses 2 NEMA 17 stepper motors attached to 3D printed front wheels, which determine the overall movement of the rover, and the back wheels are just used for stability. The stepper motors are powered by 12 AA batteries, adding up to 18 volts. They are driven by 2 L298N motor drivers, allowing the pink board to dictate precise movement via its GPIO pins. The system utilizes an MPU 6500 6-axis IMU, combining a 3-axis gyroscope and a 3-axis accelerometer, allowing the rover to move in line with the maze grid and autocorrect itself to turn exactly 19 degrees. This sensor communicates with the board via the I2C protocol, providing the real-time feedback necessary to keep the rover's exact position accurate. Thank you for watching our video.